So in the tutorial 2, we'll start with the AutoCAD drawing. As earlier in the PPT, we have discussed that we'll be integrating AutoCAD with GeoStudio. So earlier we have seen that the geometry, which will be very similar to the tutorial 1, is will be basically drawn in AutoCAD, and then we'll import this geometry in the GeoStudio. So this is a simple geometry. So let's without any delay start creating it. So we'll start line tool. You can also go with polygon tool. There are several other options, but I generally use line tool, and with that we can just create the outline and then create the border of the outline. So with the first point origin, which will be 0, and tab 0, enter. So we have selected the first point of our construction. So here, now as you remember the geometry, or you can visit back the slide, you have to select a point 70 meter on the I guess right side at an angle of 0 degree. So 0 and enter. So that's the point. Now again we'll zoom extents, clicking on the top, and again we'll go vertically upwards for a distance of about 30 meter at an angle of 90 degree. So we'll click here, and you can see that our geometry is almost up with the final extents. Now for the top surface, we'll have a 20 meter at an angle of 180 degree, as you can see, and clicking on enter. But we don't know the final point where we will be finishing our geometry, so we'll just click on escape. So after this we'll create a new line starting from the origin. So starting from the origin, we'll go vertically upwards at a distance of 15 at an angle of 90 degree. So click here, enter, and then again 15 meter at an angle of 0 degree horizontally rightwards. So that's what we'll do, clicking here and then joining the final point. So this is the now clicking on escape, and we see that we have a final geometry basically outline. Now as we have seen that there are two soils, soil 1 and soil 2, so we have to create a division again. So this division we will create again, selecting the line tool and extending the line and joining it with the vertical line, vertical boundary, and doing that we have created the final geometry. Now we have to create this line segments which we have created to enclose as a polygon. For that we'll go to type a command section, and here we'll type BO. So small BO will bring several options, but we'll select the boundary option. So boundary option will basically this command will create a boundary based on island detection technique. So if we click on a point enclosed by some line segments which are connected to each other without any gap, we can just create a polygon out of it. So just click on OK, and we click a point which is internal of the soil, bottom soil section. Click on it, and you can see that highlighted section is the blue one, and here we can just click on enter, and this will be automatic generation of a polygon. Again we'll do the same command BO and selecting the boundary command, again with the same method, clicking on OK. We'll click on the internal section, internal point, any internal point of the upper soil layer, and click on enter. So the highlighted part will be again generated as a polygon, and that's how we can create the geometry. So I'm just going to save this geometry now. Let's save this, save as in the this folder. We'll call it test geometry, and we'll save this geometry as a design exchange format of 2013. So for checking any backward compatibility issues, we can save it as an older version. It will be safer anyway. You can go with 2018 version, it's anyway older, but a little bit older version will do no harm. So we'll save it as a 2013 design exchange format, because design exchange format can work for any other softwares like FreeCAD, QCAD, and any other type of software which if you are not if you haven't installed AutoCAD so you can use other softwares. In those software you can basically save it as design exchange format. So AutoCAD is not free, but it is available for free for students, and 30-day trial is available. So if still any of you is not able to download it, then you can just use any other software and save it as DXF or design exchange format. So let's just save it, and we'll import it in GeoStudio. So after this we'll move on to the GeoStudio section. So as earlier we have created a file called test.gsz. Now we'll create a new file. We'll import the drawing which we have created in AutoCAD, and we'll have the settings of metric template and the 2D geometry. We'll select slope W analysis. Just by clicking on it we can create an analysis. So as previously what we have done is that we have created it one by one, adding 2D geometry and slope W analysis. Now we can just do it from the startup. We'll go with the default setting of side function of half sine, but we'll add a PWP condition of piezometric line, because today we will learn in this tutorial we'll learn about piezometric line as well. As earlier we have only used the RU. So RU and piezometric lines are the two important parameters which you should learn to be used as a pore water pressure condition definition. Now for the staged pseudostatic, we'll again go with the effective stress strength, and partial factors are the default. And for the slip surface, as you have seen the geometry, our slip surfaces will be moving from right to left, so we'll click on right to left. And earlier we have used the slip surface option of entry and exit method, but in this tutorial we will be using grid and radius method. So we'll click on grid and radius method, so that we'll learn both these options to be used. So in entry and exit, we actually defined the entry and exit of slip surfaces, but in grid and radius we'll define a grid out of which the center point or center of the circular arc which will be cutting or which will be causing the failure of slope will be selected, and based on that the radius can also be selected out of the geometry. So this is more randomized than the entry and exit. However, you can always go with both of this. Block specified and fully specified type of slip surface creation will only work if you know or if you have the idea of how your slip surfaces will going to occur. Otherwise, for randomized slips factor safety calculation, which are the most general cases, you should always adopt entry and exit or grid and radius method. And with the distribution and advanced analysis similar to the default, will not do anything else, change anything else. We'll just change the slip surface to grid and radius and analyze pore water pressure condition using piezometric lines. So we'll just name this analysis test 1, because earlier the analysis was the previous tutorial was named as test. So let's click on close. So what we will do now is that we'll go to file and we will click on import, and we already have saved this test.design exchange format, and click on OK, and by clicking on it we'll click on open. Because we have created the boundary polygons, the layer number 0 is there visible here. Otherwise, if you haven't created the boundary polygon, your layer number 0 will not be visible. Now with the default options, we'll import this drawing as CAD drawing, AutoCAD drawing. There are other options like MapTech Vulkan drawing, but we'll not go with that because we have used AutoCAD. And one more thing which I want to mention here is that you can also situate or position your geometry based on origin. So whatever origin you want to select, you can select it according to your own. Otherwise, you can import the coordinate system by translating the horizontal and vertical to 0, 0. So that's what I am going to do. So this whatever geometry we are importing will be origin situated like this, and by clicking on OK, you can see that our geometry has been imported. You will hover over the point number 3 is the origin, point number 4 is the 0, -15, and so on, 17, -15. So every geometrical aspect is the length is similarly in meters, as we have mentioned in the lecture slides. Now the part which we'll also learn in this tutorial is that how different material definitions can work differently in factor of safety analysis. So now what we have to do is that we have to go to define, and we have to go to materials. So we have two materials now, the soil number 2 at the upper layer and soil number 1 at the bottom layer. So soil number 2 definition is quite similar to quite simple. We'll call it soil 2 and with an underscore, and we will use the more column model because earlier we have used this similar more column model. So we'll use the 20 parameters, 20 unit weight, 20 cohesion, and 20 internal angle of friction, basic C5 soil. So that's what we'll be selecting here. So this is soil 2, which will be used for upper layer. This is there is not a lot to it. We can change color. There is not much to it, but the main discussion is about the soil number 1. So because this soil number 1 is defined in the terms of sigma and tau relationship, so let's rename it first, the soil number 1. So there are two options which we have mentioned in the lecture slide that we can go with. Simplified, there are actually three options: simplified more column, in which we can just fit a linear curve and calculate the C and phi value, which we automatically rejected because using that will be much simpler. But using shear and normal function or bilinear will be other option to follow. So first we'll use shear and normal function using constant unit weight of 20, and normal and shear function is not defined yet. So we'll go into this 3 dots and define it as a linear function. So we'll add a function. So we'll call it linear, or just tau sigma, and with that name we'll use a normal shear spline data point function. So we'll keep on adding points. So if you can visit the slide again or you have noted down the values, you can just input the sigma value and shear stress value in kilopascal terms, which we have already mentioned in the slide table. So it will be here 0, 0. We'll add it now. 75.46 will be other point, and 58.6 will be the shear force respective, and the third point 147 and 105.55. So that's our tau and sigma relationship. I am not adding the last point or the fourth point, which is 221.1 and 139.1, because in the bilinear relationship there will be a problem, because in bilinear relationship this 3 point will only decide the property. So if you want to compare bilinear with shear and normal strength function, then we have to keep them uniform. We don't want to make them trilinear. If we add the last point, this line segment will become trilinear, and the bilinear fitting will be problematic in that case. So we'll go with this 3 point only and click on close. So we have the tau sigma function, as you can see here, and with that tau sigma function we can define the soil 2. So we can create a new material, add new material here as well. So with this new material will be soil 1 by linear. Okay. So we'll create a bilinear material, selecting the bilinear material model. The unit weight will be again 20, and the phi 1 which I have calculated based on the geometry of this bilinear, and I have also mentioned the plot while going to the PPT. How can we calculate this phi 1, phi 2, and normal and cohesion? So the cohesion will be basically 0, because the origin point of sigma and tau is 0, 0. So the phi 1 will be, as I have calculated, will be 37 degree, and the phi 2 is 33 degree, and the normal at which the line is taking the turn for the bilinear will be 75.46 kilopascal. So these are the parameters for bilinear. So we have created all this. Let's just change the color of it to somewhat bluer, so that we can differentiate it. So the red one is the soil 2, and the blue and green are the soil 1 bilinear and soil 1. So we have created 3 different material properties. So we'll do a case study or a parametric study by changing this soil 1 bilinear and soil 1. Let's just rename this soil 1 as tau sigma, so that we can differentiate it later on. So we have 3 soils with us. Soil 2 is basic more column, soil 1 tau sigma, and soil 1 bilinear. But now we'll close this, and we'll define the soil material later on. So after defining the material properties and looking into the exporting the geometry and all, we'll define the material properties, and we'll go to draw, and as earlier we have done, we'll select the material. So the as we have already known that we have 3 material, The top material is soil 2, so we'll just go with the soil 2 now and select the top portion. And for the soil one, you should just decide with which model you want to go. So I will go with the bilinear first. So I have chosen bilinear model and clicking on the bottom surface or bottom area. So now the definition is complete, the material definition is complete. The remaining things are basically to define seismic loads, which we earlier we have defined as 0.15 and 0.1. So one more thing I would mention here is that you can calculate this horizontal and vertical seismic coefficient based on location or seismic zones in which our country India has been divided. But if any foreign standard or other standard require you to calculate it differently, you can follow that. Basically in Indian standard 1893 part 1, you can look up for the seismic coefficient definition this based on structure as well. So now with these dummy values we can move on and start solving our problem. Now before going to any other part, we have to define the pore water pressure parameter. So we'll just go here and we'll add a piezometric line. This line will be applicable to all three of them. Now these points are needed to be added. So we'll click on add. We'll just have created one piezometric line. What we can do is that we can rename it, but just go with the number 1. Now I'll just close it and we'll go to draw, and in the draw section we'll go to pore water pressure parameter. Because we have selected a piezometric line number 1, we'll start drawing. So we can just select any dummy drawing. Let's assume that at an height of 15 meter, a 1 meter or 2 meter low piezometric line will be there. So we'll start drawing and we'll select a point about at a depth of 1 meter from the 15 meter. You can see when I hover, you can see the coordinate system. So I'll go to 14 and I will just create a straight line at some distance like this. And what I will do is that I will just merge this straight line just under this point 50, 15. So 50, 14 will be the second point of the piezometric line, and the end point will be the toe of the slope. So finishing it here and clicking on escape. So this blue line will be the piezometric line, which is the phoretic line, and I don't want to go deeper, but it's very like it's just the phoretic line. So this shows how your water seepage will take place along this line. So I'm just going to close the actually once I clicked on escape, it's automatically closed. So this piezometric line is defined. Now after this piezometric line definition, what we can do is we can go and draw the slip surfaces based on grid and radius. So let me just select the grid first. So I'm just going to zoom out a bit. So so for the grid creation, we have to select a grid like this. So you can create a number of increment about 10 and 10 here. So like that you can create a grid, and your circle, cutting circle will be between this grid somewhere, whatever intersection points which we have created, this intersection point will cover those point. You can fine tune this analysis. There are more options, but I'm going to go with this dummy analysis and I'm just going to close it. Now we have to draw radius. So this grid and radius are the only 2 points which you require to be created in this method. Now for the radius, you can select any point from here to the top. So this is the radius. Now I want to create an increment of 10. So 10 by 10 by 10. So total number of 1000 increments will be there. And if you want to rotate it, you can rotate it as well. So like this or this, but I generally go with this kind of like parallel to the slope radius, so that it will be more in tune with the actual slip surface. So I'm just going to close it now. So this is our radius and this is our grid. So grid, whenever this grid we create various cutting circles will intersect with the circles, and that's how multiple critical or multiple failure surfaces will be created, and the lowest failure factor of safety will be calculated based on this combination. So this is the final definition of our model, and nothing else needs to be done. So I'll just save this model, and in this folder I'm just going to call it test1 and click on save. So after saving this, I will just start the analysis, and after starting we'll wait for some time, and in a millisecond or picosecond the results are here. So you can see the lowest factor of safety is 0.799, and here you can also see the center or x and y coordinate of the factor of safety, and you can also see that your by various calibration and various hidden trial, you can see this red part is the major section where failure is occurring. Okay, so this red part is the very dense zone of failure. So you can also recalibrate your grid and radius to come up with a location much critical than this location. So you can see that in this zone of red you will see a lot of failure surfaces, and the failure is quite similar to the previous case, and the factor of safety is now a little bit smaller, 0.799. So that's what we have seen in the bilinear analysis. So I'm just going to save this, and in the one more parametric study we will try the tau and sigma relationship. So after looking into the bilinear model, we'll again go to the definition part. So here we are in results part, so we'll switch the context to definition part again, and in definition part we'll just go to the draw material part, and there is nothing much to do. We'll first remove the material of the bottom layer. So now from the clean slate part we'll use a tau sigma material. This is the green one, so as to differentiate the color. Now with that material, keeping everything same, you must be remembering the critical factor of safety of 0.79 and so on. Now we'll again run the analysis. So just to check out the analysis, yeah, here there is a slight difference of 0.803 which can automatically be ignored because the friction angle and phi 1 and phi 2 in bilinear model were taken with a they were rounded off. So I guess there is not a lot of differences in this material models if you are using this bilinear as well as tau and sigma relationship, and maybe there might come a difference if you want to simplify this material models into more column simplified by fitting them tau and sigma data linearly and creating some C and phi data. Otherwise there is not a huge difference, and this difference can also be this initial factor of safety of critical surface. I guess the point is also at the same location which we have seen here, 0.803. So let me again run this model for you. Just remember this is the point of 803, and we are getting the FOS for this part. And let me just go to definition model again, and just to recheck it, we'll go to the draw material region, and first remove the bottom region and again reassign the bottom region as the bilinear material. Close it and start the run, and we'll see that 0.799 will be again about at the same point, and the failure surface however a little bit larger, but yeah, 803 is available, but this 0.799 is also available in that case. But this difference, I can assure you that this is not a huge difference. And let me just again go to definition module and go to define material part and see the bilinear properties. This 37 phi 1 and 33 phi 2 are basically the rounded off values of phi. So 37.23 and 33 point something was the actual value, and this small rounding off error will also be causing some change in factor of safety of critical surface. However, in tau and sigma, what we have done is that we have added the actual points, and if we add the third point as well, there will be a huge difference which you have to consider on your own and do it as a homework problem. So in today's in this part 2's tutorial, we have seen how different material model and grid and radius type of factor of failure surface analysis, and basically this project control with piezometric line pore water pressure parameter effects. You can also remove this piezometric line using it as none and close it, and you will see that this piezometric line has automatically disappeared. And we'll just start the analysis and see how does the analysis differs. So you can see the factor of safety has been drastically increased, and it has come up to 1.169. So you can see the effect of water, pore water pressure, and these parameters can affect the soil properties a lot. So whatever we are doing, whatever we are considering in any geotechnical situation or any geological situation affects the whole factor of safety a lot. So you have to be considerate of that in that case. So, and you can also, maybe in later tutorial we can also go to definition, and we can also change this finite element analysis parameters, like we can change the number of slices to 30 or more, and number of iterations to 100 or more. But maybe in this tutorial it is enough. So we'll finish this part 2 of GeoStudio tutorial here.